Hello and welcome back everyone. Today we're covering day 13, notes on interest. We're also going to be looking at other applications of exponential functions. So here's question 1. It says when a person takes a dosage of I milligrams of ibuprofen, the amount A in milligrams of medication remaining in the person's bloodstream after T hours can be modeled by the equation A equals I times 0.71 raised to the power of T. Now the I represents the initial amount of the ibuprofen that is in the bloodstream. The 0.71 represents the fact that it's 71% of the initial amount that will be remaining after every hour. And the T is the number of hours that have passed. So let's look at question A here. Find the amount of ibuprofen remaining in a person's bloodstream for the given dosage and elapsed time since the medication was taken. So in question A, the initial dosage is 200 milligrams and the time passed is 1.5. That's 1.5 hours. So we start with the equation. A equals I times 0.71 raised to the power of T. And again, I is going to be that initial amount, so that's going to be the 200. 0.71 represents the 71% that's left after each hour, and the T is the number of hours, so we're going to substitute 1.5 for T. All right, and then we just put all of this in our calculator, and we get our amount. That's 119.65 milligrams. That's how much ibuprofen is left in the bloodstream after 1.5 hours. All right, and likewise, here's part B. The initial dosage is 325 milligrams, and the time elapsed is 3.5 hours. So we'll just simply rewrite the equation. A equals I times 0.71 to the T. Replace I, which is the initial amount of the ibuprofen. That's 325. And we replace T with 3.5 hours and put it in our calculator. And we end up with 98.01 milligrams. So what does all this mean? That means if we start with 325 milligrams of ibuprofen in our bloodstream, after 3.5 hours, we would have 98.01 milligrams left. All right, and for part C, likewise, we begin with a dosage of 400 milligrams and the time passed is 5 hours. Here's our equation. We replace the I with the initial amount of 400 and replace T with the 5 hours. Put this in our calculator, and so after 5 hours, we would have 72.17 milligrams of ibuprofen left in our bloodstream. All right, here's question 2. It says, bike costs. You buy a new bike for $200. The value of the bike decreases by 25% each year. Write a model, which is just a function or an equation, giving the bike's... All right, here's number 2. Bike costs. You buy a new bike for $200. The value of the bike decreases by 25% each year. Write a model giving the mountain bike's value in dollars after T years. Okay, so we know the initial amount is 200, so that's what we're starting with. And you're going to multiply it by 0.75, and here's why. You are decreasing the value by 25% each year. So if you subtract 25% from 100%, that leaves you with 75%. So at the end of each year, the value is 75% of what it was in the previous year. So that's why you're multiplying by 75% here, or 0.75, and we're raising that to the power of T, which represents the number of years. So this is our equation, 200 times 0.75 to the power of T. All right, we're not going to worry about graphing this, so let's go to part C. Estimate when the value of the bike will be $100. So we take this equation and we set it equal to 100. So 200 times 0.75 raised to the T is equal to 100. We're going to go ahead and divide by 200 on both sides. And we know that 100 divided by 200 is 1/2, or 0.5. Now we can solve for t, the exponent, by converting this into log form. In log form, it would be log base 0.75 of 0.5 is equal to t. And now we just put that in our calculator. There's two ways to do it. You can do the change of base rule, and that would just be log 0.5 divided by log 0.75. Or you can just go into your calculator and go into the math menu. Let me show you. All right, so got my calculator pulled up. Like I said, if you use the change of base rule, you would do log 0.5 divided by log 0.75. So let's do that. Log 0.5 divided by log 0.75. All right, and I'm just using this log button right here. All right, press enter and you have your answer. All right, now the second way is to go into the math menu. So press this math button and then go down to where it says log base, which is right here. And then you can type in the base and the other number. So the base is 0.75, and then type in the other number, which is 0.5, and press enter. And you see you have the exact same answer. So whichever one is more convenient for you. If you have a calculator that does not have this log base feature, then you will have to go with the change of base rule up here at the top. All right, so we're back here on the page, and from our calculator, t was 2.41 years approximately. So in 2.41 years, that's when the value of the bike would go from 200 down to 100. Here it is, question number 3. In 1996, there were 2,573 computer viruses and other computer security incidents. During the next 7 years, the number increased by 92% each year. What formula should be used? All right, well, the formula is going to be the new amount is 2573, that's your initial amount, times 1.92 raised to the t. Now let me explain why it's 1.92. You are increasing by 92%, which means you're adding 92% to the initial 100%. Well, what is 92 plus 100? That's 192. Convert that to a decimal. That's 1.92. So your base, or your multiplier, every year is 1.92. All right, so this is our equation. Now part B, find the value of t when y is equal to 125,000. In other words, how many years would it take for our initial amount of computer viruses to reach 125,000? So we set up this equation. We take our initial formula and set it equal to 125,000. Now we're going to divide by 2573 on both sides. And that will give us 125,000 divided by 2573 equals 1.92 raised to the power of t. Now we'll convert this into log form. And in log form, it's log base 1.92 of this fraction is equal to t. And now we can plug this into our calculator, either using change of base or by going into the math menu. All right, first I'm going to type it in just using the change of base rule. So the change of base rule says that this is going to be log of this fraction. So let's go ahead and do that. Press the log button and let's type in the fraction. It's 125,000 divided by 2573. Close that parentheses. And then all of that is divided by the log of the base, 1.92. All right, close that parentheses and press enter, and there is our answer. Let's also do it the other way. Let's press the math button choose this log base option, type in our base of 1.92, and then type in the fraction, 125,000 over 2573. And as you can see, we get the same answer. Alright, so we are back on the page, and you saw that on the calculator it said t was approximately 5.95. We can just round that up to about 6 years. Alright, so in other words, it would take about 6 years for the value to reach 125,000. And now part C, estimate the year when there were about 125,000 security issues. Well, we started in 1996, and 6 years has gone by, so 1996 plus 6 is 2002, so that would be the year. All right, number 4. A culture of 100 bacteria in a petri dish doubles every hour. Predict when the number of bacteria will be 350,000. All right, to write our function, first of all, we recognize that doubling means you're multiplying by 2. So if you start with 100, after the next hour, you're going to have 100 times 2, or 200. So our base multiplier is going to be 2 here. So the equation is 100, that's the amount we start with, times 2 raised to the power of t. All right, estimate the time. So the time for it to reach 350,000 is to set up the equation that 100 times 2 to the t equals 350,000. Now let's divide by 100 on both sides. That will knock off 2 zeros here, so that would be equal to 3,500. Now let's convert this equation into into log form. And in log form, we have t equals log base 2 of 3,500. Now we can put that in our calculator, and you're going to get 11.77 hours. Now question C, convert the time into hours and minutes. Well, we already know that the 11 is the number of hours, so it's going to be 11 hours plus some minutes. Well, we'll take the decimal part, which is 0.77, and multiply that by 60 minutes. When we do that, you end up with about 46 minutes. So it's 11 hours and 46 minutes. That's how long it would take for the number of bacteria to grow from 100 to 350,000. All right, and here's number 5. You deposit $4,000 in an account that pays 2.92% annual interest. Find the balance after 1 year if the interest is compounded with the given frequency. So for question A, we're compounding quarterly. Now this requires a different equation. The equation is the compound interest equation, where A is the amount, and that's equal to P, which is the present value or the principal, that would be the $4,000, times 1 plus R. R would be your interest rate, which is the 2.92, converted to a decimal, divided by N, and N is the number of times you're compounding per year. Since that's quarterly, you're compounding quarterly, that's 4 times a year, so N would be 4 in this case. And then your exponent is N times T. That would be 4 again. And then T is the number of years, which is 1. All right, so let's plug everything in. As we said, P is the $4,000 that you start with. R is your interest rate converted to a decimal. So 2.92% becomes 0.0292. And then you're dividing it by N. And N is 4 because quarterly means 4 times a year. And then the exponent is N times T, so that's 4 times 1. And it's 1 because that's the number of years, 1 year. All right, we would just put this in our calculator, and ladies and gentlemen, we get a value of $4,118.09. Now, what if it was daily? Well, we use the exact same equation, but the only thing that changes is the n. Because if you're compounding daily, that means you're compounding 365 days in a year. So n becomes 365. Let's plug in everything. The p-value is still the 4,000. Your interest rate is still 0.0292 when you convert it to a decimal. And then, as we said earlier, the n in the formula becomes 365 because it is daily. All right, we just put that in our calculator, and our value is $4,118.52. So it's just slightly more than this amount from the quarterly compounding. All right, now part C. Estimate the amount of time it takes for the account to reach $6,000 if it is compounded monthly. Okay, so if it's compounded monthly, then we have to change n again to be 12 because there are 12 months in a year. So here's our equation, and this time we set it equal to 6,000, and we're solving for t because we want to know how many years it would take. All right, so the first thing we'll do the second thing is to divide by 4,000 on both sides. And 6,000 divided by 4,000 is 1.5. Now let's convert this to a log form. And in log form, you're going to have log base 1.0024, etc. of 1.5 equals 12t. Oh, let me go back and explain the 1.00243333. That is from the value that's inside this parentheses. I just decided to go ahead and calculate this. So I just did 1 plus 0.0292 divided by 12, and it gave me this decimal here. I didn't want to round it because I want it to be as accurate as possible. So if you're going to do the same thing, do not round here. You write out the entire decimal, and then you only round at the very end. Okay, so that brings us to this equation where we have 12 times t is equal to the log. Now we'll have to divide by 12 on both sides to get t by itself. So t is going to be equal to this log, all divided by 12. And we just put that in our calculator. And let me just demonstrate on the calculator how I would type that in. I would probably just use the go into the math menu to type in this log. So let's do that. So you press the math button, go down to log base, and now we're going to type in the base, which is this long decimal here. It's 1.00243333. All right, and then the other number is 1.5, and then I'm going to come out of that, and then I'm going to divide that by 12. Okay, so there we have that, and then you just press enter, and there is your answer. So back on our page, t is about 13.9 years. All right, here's number 6. You deposit $2,500 into an account that pays 5% annual interest compounded continuously. Find the balance after each amount of time. Well, we need a new formula once again. The continuous compounding uses the Euler number E. So the amount is P, which is your initial amount, times E raised to the power of R times T. R is the interest rate, changed to a decimal, and T is the number of years. All right, and then again, P is the initial value that you're depositing. So for 2 years, we just plug in the information. We have $2,500 for P. The interest rate is 5%, converted to a decimal, that's 0.05. times t. So that's r times t. So t would be 2 years. We just put that in the calculator and let's demonstrate that. All right, we want to put in the 2500 times e raised to the 0.05 times 2. So we begin typing the 2500, and then for the e, the best way to do the e is, since you have to type in an exponent, is to use this e to the x here, which is the second operation of the ln button. So you would press the second button first, and then press the ln button, and then as you see on your screen, it has e raised to an exponent. And then you just type in your exponent, which is 0.05 times 2. And we press enter, and we have our answer. So back on the page, it's going to be $2,762.93. All right, and then for part B, we just changed the number of years to 5. So we substitute the 2 for t. We replace the 2 with 5. All right, so we put that in our calculator, and we get 3210.06. All right, and now we have 7.5 years. So we have the equation. We plug in 7.5 for t, and we put that in our calculator, and we get 3637.48. And now we come down to question D. Estimate the amount of time that it takes for the account balance to increase by $1,000. Now, if it increases by 1,000, that means it goes from the initial 2,500 to 3,500. So we set up the equation that 2,500e raised to the 0.05 t is equal to 3,500. Now we'll divide by 2,500 on both sides, and that's going to give us 1.4. Now we'll convert this into a log. Since it's base e, we're going to use ln, or natural log. So 0.05t is the natural log of 1.4. And then we'll need to divide by 0.05 on both sides. So t is the natural log of 1.4 divided by 0.05. And now we put that in our calculator. And we get t is equal to 6.73 years. All right, here's question 7. The population of a city can be modeled by P equals 125,000 times E raised to the 0.02 t, where t is the number of years since 1990. Question A, what is the population in 1995? Well, between 1990 and 1995, 5 years has gone by. So t is going to be 5. And we simply plug 5 into this equation here for t. All right, so P is 125,000 times E raised to the 0.02 times 5. And when you plug that into the calculator, you end up with this value, 138,146.4. And that means approximately 138,146 people would be the population in 1995. Question B, estimate the year when the population reached 200,000 people. So we set the equation equal to 200,000. Then we'll have to work backwards to solve for t. First, let's divide by 125,000 on both sides. So 200,000 divided by 125,000 is 1.6. Now we'll convert this equation into a log equation. Since it's base e, you're going to use natural log. So natural log of 1.6 is equal to 0.02 times t. Now to solve for t, we'll have to divide by 0.02 on both sides. And so t is the natural log of 1.6 divided by 0.02. We'll put that in our calculator and we get approximately 23.5. That's the number of years. But the question says estimate the year when the population reached 200,000. So we know that 23.5 years has gone by, and that's starting at in the year 1990. So if we add 1990 plus the 23.5 years, that's going to get us into the middle of the year 2013. And here's our last question, number 8. When a plant or animal dies, it stops acquiring carbon-14 from the atmosphere. Carbon-14 decays over time with a half-life of about 5,730 years. By the way, this half-life means that it takes 5,730 years for the carbon-14 to decay to half of its original amount. All right, then it says the percent P of the original amount of carbon-14 that remains in a sample after T years is given by this equation. So that's 100 representing 100% at the time of death times 1/2 raised to the power of T over 5730. All right, question A. What percent of the original carbon-14 remains in a sample after 2,500 years, 5,000 years, and 10,000 years? All right, with the 2,500 years, all we're doing is replacing the T with 2,500. So it looks like this. So you'll have 100 times 1/2 raised to the 2,500 over 5730. Putting that in the calculator gives us 73.9%. So that means after 2,500 years from the time of death, you would have 73.9% of carbon-14 left in the body. All right, what about after 5,000 years? Well, just substitute T with 5,000. And this is what it looks like, and then the answer is going to be 54.6%. So after 5,000 years, you would have 54.6% of the carbon-14 left in your body. Likewise, after 10,000 years, just replace T with 10,000, and you get 29.8% of carbon-14 left. All right, now question B. An archaeologist found a bison bone that contains about 37% of the carbon-14 present when the bison died. Now, I'm thinking that this might be a typo, a typing error. I'm thinking that 37% of the carbon-14 is left when the bison was found. Because at the time of death, the amount of carbon would have 100% at that time of death, as the equation here indicates. So I believe this 37% is how much was left when the bison was found, not when it died. All right, I'm going to skip the graph part, and let's go to where it says estimate the age of the bone when it was found. Well, to do that, we take the equation here, the original equation, and set it equal to 37. Then we'll divide 37 by 100, giving us 0.37. Then we'll change this into log form. So that would be log base 1/2 of 0.37 equals T over 5730. Now to get T by itself, we would multiply by 5730 on both sides. So T is 5730 times log base 1/2 of 0.37. Well, we can put all of that in the calculator, and that's going to give us 8219.1 years. So over 8,000 years is how long it would take for the bison bone to have reached 37% of its carbon-14 content. All right, so that's how old it was when the bone was found. All right, that's going to conclude the notes for this particular lesson. Now you're able to get started on your homework.